Hi all, welcome to lecture 11 of this lecture series named Unconstrained Optimization. Today we'll discuss certain line search techniques. But before we start with the lecture, let's recall what we discussed, certain definition and results that we discussed in our previous lectures. So first let us discuss what is an unconstrained minimization. Let f be some function from n-dimensional real set to scalar value, then minimization of fx such that x belonging to the whole of Rn is unconstrained minimization. Basically, there is no constraint on x here. There is no constraint on x, and x can take all of its all the real values. So then this is called unconstrained minimization. So let's discuss what is local minimum. So let's x star be some point in Rn such that it is a local minimum of f if there exists a delta greater than 0, a positive value delta, such that fx star is less than fx for all x belonging to a ball of radius delta centered at x star. So let's say x star is a point that we want to check if it is a local minima. Then if we can find a delta, a small, it can, however small it can be, but it has to be positive, and we draw a ball of radius delta around x star, then all the values of x inside this ball, if they are smaller or than or equal to fx star, let's say fx star is less than or equal to f for all fx in this region, then x star can be set as a local minima. Now descent direction. So what is a descent direction? So let x bar be some point in the domain of f if there exists a direction d and a positive value delta such that the value of fx bar is greater than value of fx bar plus alpha d, where fx bar plus alpha d denotes let's look at it as in terms of diagram. Let's say this is x bar and d is some direction. Now let delta be some scalar values, positive scalar value. Then if fx bar is greater than the function value in whole of this line between x bar and x bar plus alpha delta d, if fx bar is smaller than all of these, greater than all of these points, then this direction d is said to be a descent direction. Okay, this is the qualitative definition of d, but how do we check whether a given direction d is a descent direction or not? So there is a simple test to that. So there are certain assumptions that require for this test to happen, is that f should be continuously differentiable and x should belong to Rn x bar. Then if g x bar transpose d, basically the dot product of the gradient of the function at x bar and the descent direction, if it is less than 0, then d is a descent direction of f at x bar. This is a simple test. Now after that we discuss basically three conditions that help us determine whether a given point is a local minimum or not. There were certain sufficient conditions and there were certain necessary conditions. Let's look at them one by one. So first of them is first order necessary condition. So first order means we use the first derivative information of the function, and necessary condition means that if a given point is a local minimum, then these conditions should be followed. So what are these conditions? So if f is some real valued multivariable function, multi-input real valued function, and f is continuously differentiable, then x star, some point x star is a local minimum if the gradient of the function at that point is 0. This condition is generally used as the stopping condition in the minimization algorithms. That is its utility. Now let's look at the second order necessary conditions. Again, we assume f is some real valued function, and here, because we need second order information, we assume that it's twice differentiable. Now the point x star is a local minimum if gx star is 0, or basically the gradient is 0, which comes from the first order necessary conditions, and the Hessian of the Hessian of the function at x star is positive, should be positive semi-definite, will be positive semi-definite if x star is a local minimum of f. These are some necessary conditions. Now let's look at the sufficient conditions. So these necessary condition will help us determine, if someone gives us a point, we can check whether it is a local minimum or not, but these are not very useful in like we cannot find x star if the local minimum if nothing is given. For that we need something sort of a sufficient condition. So there is a second order sufficient conditions in which if f is a real valued function, multivariable input real valued function, and f is twice differentiable, then if its gradient at x star is 0 and Hessian is positive definite at that point, then x is a strict local minimum of f. So these are the sufficient conditions. So using these three conditions, we defined a algorithm, minimization algorithm, in which first we initialize x naught. Basically we set the initial value of the input variable and the iteration variable to 0. Then we run a loop in which is run till the stopping condition is not satisfied at xk. We find a xk such that we find xk plus 1 such that the function value of xk plus 1 at xk plus 1 is less than fxk. We increase the iteration variable, and this loop continues till the stopping condition is satisfied, and then the x star is equal to the final xk, which is the local minimum of fx. This is the general framework or general outline of an unconstrained minimization algorithm. But there are certain questions that this algorithm triggers. That how do we find xk plus 1 in step 2a? Basically in this step, how do we find xk plus 1? Second question is, which stopping condition can be used? What is a good stopping condition? So as we discussed earlier, first order necessary condition is generally used as a stopping condition. We'll look at it later. The third question that we can ask is, does the algorithm converge? And if yes, how fast does it converge? So basically we are asking about the convergence and the rate of convergence of the algorithm here. And if the algorithm converges, does its speed depend upon the initial condition? So what are the effects of the convergence on the initial condition of the initial value that we take of the variables? So in today's lecture, we'll try to answer some of these questions, and we'll keep refining the unconstrained minimization algorithm so that it formally answers these questions. So with that, let's start with today's lecture. So first, let's start with the first thing, that is stopping condition for the minimization problems. So ideally, the stopping condition would be that the gradient of the function at the current iteration point should be 0, and the Hessian should be positive semi-definite. These are the ideal stopping condition that it should be, but practically it's very difficult to keep on calculating the Hessian. So for practical purposes, the Hessian is generally ignored. We do not check the positive semi-definitivity of the Hessian. Rather, we only check the gradient, and that should be less than some very small value epsilon. Okay, there are certain other stopping conditions as well, like gxk should be less than equal to epsilon 1 plus mod of fxk, or fxk minus fxk plus 1 upon mod of fxk should be less than epsilon, some small value. So in this course, we'll use this stopping condition. You can use whichever, you can use others as well. They have their own, they have their reasons why to, in which you decide which stopping condition to use, but for simplification, we'll use the first stopping condition, and for most of the purposes it works really fine. Okay, so this was how what stopping condition should be used in the minimization algorithm. Now let us look at the speed of convergence. So for speed of convergence, let's assume that optimization algorithm generates a sequence which converges to X star. Okay, so the question is, how fast does the sequence converge? How fast does it converge? Okay, so to answer this question, we'll have to define certain parameters related to speed of convergence. So we'll first define them. So the first thing is the order of convergence. So what is order of convergence? The sequence xk converges to X star with order p. if limit of k tending to infinity, that is iteration tending to infinity, norm of xk plus 1 minus x star divided by norm of xk minus x star to the power p is equal to beta, where beta is some finite constant. Okay, so if this relation holds, then we say that the sequence converges to x star with order p. Please note, order is in the power of the denominator. Okay, this statement asymptotically means that xk, if xk is very large, let's say, should be equal to some beta times xk minus x star to the power p. Okay, which means two things. The first thing that it means, please note that beta here is called convergence rate. Okay, now this relation tells us that higher the value of p, right, faster is the convergence. Yeah, how can we say that? So let's say xk and x star are close together. If p is xk and x star is such that they are close, so the norm is less than 1, and if it raises to the power p, this whole value shrinks. So higher the value of p, lower is the value of this value, and hence xk plus 1 is more closer to x star. I hope that makes sense. So if higher the value of p, faster is the convergence. Please note, the problem here is, like, if xk is not very close to x star, let's say the difference is greater than 1, then if we increase p, the xk plus 1 will diverge, so algorithm won't converge. So this is just true. Higher the value of p, faster is the convergence if the algorithm converges. The initial value is closer to it somehow, like it is not always true, but it is true if the algorithm is going to converge. We'll get to that later, but this is a general idea that higher the value of p, faster is the convergence. Okay. Now let us look at some types of convergence, like linear convergence, quadratic convergence, etc. So first of those is linear convergence. So okay, so when is something a linear convergence? Where order is 1 and beta lies between 0 and 1. Okay. When this is true for some algorithm, we say the algorithm converges with linear convergence. Okay, so some examples. Like, let's say beta is 0.1 and the initial value of the input is taken such that it is 0.1. Okay, then how the norms of xk minus x star evolve over in each iteration, we can see that First will be 0.1 when k is 0. When k is 1, it will be 0.01, which is 10 to power minus 2. Then it will be 10 to power minus 3, and so on. So it is getting reduced. Basically, over time, k is coming closer and closer to x star. Now let's take a look at some other example where beta is 0.9 and the initial condition is such that it is the same as previous one. So now how do the norms evolve in each iteration now? Xk minus x star. How do they evolve now? So it will again start with 0.1, but now it will be 0.09. Please remember, how did this come? That we said that xk plus 1 asymptotically is equal to beta times xk minus x star. This is how we are getting this. Okay. Then what will happen next? 0.09 will become 0.081. I think it will be 0.0081 if I'm not wrong. No, it will be 0.08. Yeah, because this gets multiplied by this, right? So yeah. Then again, what it will be? 0.81 multiplied by 0.9. 0.081 multiplied by 0.9 is 0.0729. So you can see it's not reducing as fast as the previous one. Here you can see in first iteration both have the same distance. Xk is at the same distance as x star as in the second case. Second, it's 0.01 and it is 0.0. It's 9 times that value. Here it's 0.001 and it is 81 times that value into 81 into 9, and here it will be 0.0001 and this will be into 729 times the value. So here the convergence is not as good as the previous one, which means we can conclude one thing here, that in linear convergence if beta is close to 0, then xk minus x star goes to 0 faster than when beta is close to 1, which in shorthand terms means beta near 0 implies faster convergence. In linear convergence terms, this is better. Alright. So this is the example of linear convergence. There is one more. There are several other types of convergence. The second one is quadratic convergence. Alright. So what is quadratic convergence? Here the order is 2 and beta is anything greater than 0. Basically, convergence rate is anything greater than 0. This is how the quadratic convergence is defined. Let us look at some examples. If beta is equal to 1, let's say beta can be anything greater than 0. Let's say beta is equal to 1, and x naught minus x star is 0.1. Right? Then how do the norms of xk minus x star evolve over time? So it's 0.1, and it's so remember what the formula was. But here the order is there, so it will become 2. Okay, so 0.1 square into beta is basically, you keep on doing square for this, so 0.01, then it will be 10 to the power minus 4, then 10 to the power minus 8, etc. So you can see it is the convergence rate is higher than convergence rate in the linear case. It's clearly visible, but as some of you might have seen it already, it has some flaw. That because beta is equal to 1, if x naught minus x star is greater than 1, let's take it as an example. So let's say beta is equal to 1 and x naught minus x star is something greater than 1, let's say 2. Assume, let's say it is 2. Initial condition is like that. Then how do the norms evolve over each iteration? Then first error will be 2. What will be the second error? It will be 4, then 16, or 16, and then it will go on. So basically you can see that the norms are diverging. Xk is getting farther and farther from x star. So that is one problem with quadratic, which we can write it clearly here, that here beta is 1. Please note it can be anything greater than 0. So beta is greater than 0. So x naught minus x star should be less than 0. Should be less than 1 for convergence. Right? Which in turn means for quadratic convergence, initial point should be close to local minimum for these types of algorithms to converge. For these algos to converge. Alright, so for quadratic, it should be, for quadratic, the initial position should be closer to local minimum. Please note it's not in the case with linear convergence, because even if it is greater than 1, because your beta is between, because even if this is greater than 1, because your beta is between 0 and 1, with time and the algorithm should converge, even though it will be very slow, but it will, you can talk about some guarantees. But on the other hand, in quadratic convergence you cannot, if beta is, let's say, 1 or greater than 1. Alright, so yeah. Now there is one more kind of convergence that we'll talk about. It's called superlinear convergence. So these are the qualitatively, if we say, these are the types of convergence that are faster than very fast compared to linear, but not as fast as quadratic. This is just qualitative way of thinking about superlinear convergence. It's very fast. It's faster than linear, but it's not as fast as quadratic. Okay. So, but let's define it formally. What it means. So, suppose algorithm generates a convergent sequence xk. So the algorithm generates a sequence of the initial the points xk. Then, if limit k tends to infinity for xk plus 1 minus x star and xk minus x star is equal to 0, which means that the distance between xk plus 1 and x star is significantly smaller than, is very very smaller compared to xk plus minus x star, which means that it is faster than linear very very fast compared to linear convergence. And limit k tends to infinity same thing but with second order is infinity. So basically if I square it up, it becomes infinity, which is, it is slower than quadratic. It is not as fast as quadratic. So I can write it here, faster than linear, slower than quadratic. Okay, so this is called superlinear convergence. Now let us look at some of the sequences that can be described at converging sequences, which can be described and look whether they are linear, quadratic, or superlinear. Okay, so I'll just give you some examples. Okay, first one is sequence such that xk equal to 1 plus a to the power k, where a is between 0 and 1. So what about this? So to what point will it converge? If a is between, as k tends to infinity, let's say, to what point this should converge? So this converges to 1. Alright, this converges to 1. Now, how fast does this converges? So let's do some analysis of convergence. How fast does this converge? So what is x naught is equal to 2, right? Because k is 0, a to the power 0 is 1, which means it's 1, which means plus 1 if you'll do, it will be 2, right? So x naught is 2, which means x naught minus x star is 1, right? Now what can you say about xk minus x star? Let's say what is x1 minus x star. Okay, so what is x1? x1 will be 1 plus a minus 1 mod, which will be a, right? Then how will be a to x star x2 minus x square minus x star is equal to 1 plus a square minus 1 is equal to a square, which means x to the power k minus x star should give you a to the power k, right? Correct. So we can see that what will be xk plus 1 minus x star? A times ak, right? Which means a times xk minus x star. Correct. Here, so by this analysis we can see that order is 1 and the convergence rate is a. Okay, and this is a linear convergence. So this is, so x the sequence 1 plus ak, where k tends to infinity and a is between 0 and 1, is a linear convergence. It converges to 1 and with order 1 and beat convergence rate equal to a. It's a linear convergence. Now let us look at some other convergence, another sequence like this xk. Let me change this color to white. Alright, so xk equals to a to the power 2k. Okay, where a is again between 1 and 0. So a is less than 1, but it is positive. What will this converge to? Let's say k goes to infinity. So it's 2 to the power k, not 2 into k, it's 2 to the power k. Okay, so what will, as k tends to infinity, 2 to the power k tends to infinity, and because a is less than 1, this will go to 0. So converges to 0. Alright, now let's analyze its norm. So what is x naught here? X naught will be a, right? Because here x star is 0, mod of x naught or xk minus x star will be same as mod of xk, right? And because a is positive, any and to the power, and k is also always be a positive number, so xk will always be a positive number. All right, so so basically here the norm of xk minus x star is same as xk. So what is x naught minus x star? Basically it is x naught, which means it's a. Which is x1 minus x star? It is x1, which is 8 square. Which is x2 minus x star? It is x square. It is just as x2, and which means it is a to the power square, which is a to the power 4, right? And similarly, if you'll go on, xk minus x star is equal to, what does it equal to? Xk, which means a to the power 2k, a to the power 2 to the power k. All right, and the same series, what is xk plus 1 minus x star? It is equal to xk plus 1, which is equal to a to the power k plus 1. All right, which you can write as a to the 2 dot to the power k. Basically you can write as a 2 to the power k whole square. Alright, so this you can write. Here you can see that this is equal to xk plus 1. So x star is equal to 1 times xk minus x star, which is equal to a to the power, which is equal to a to the power 2 to the power k the whole square. So this is a quadratic convergence, so where order is 2 and beta is 1. So it converges to 0 quadratically with beta equal to 1. Okay. Now let us look at one more sequence, one more sequence where xk is 1 plus k to the power minus k. Just before this is an example of superlinear convergence. How? Let's check. So let's check what is xk minus x star. Okay, here what is x star? What will the sequence converge to? So as you can see, k to the power minus k, where k goes to infinity, means this whole term goes to 0, which means x star is 1. Alright. So what will be xk minus x star? It will be k to the power minus k. Right. It will be xk plus 1 minus x star. It will be k plus 1 minus k plus 1. Alright, which can be the k to the power minus k can be written as 1 upon k to the power k. This can be written as 1 upon k plus 1 to the power k plus 1. Alright. Now let's check for linear convergence. So limit k tends to infinity, xk plus 1 minus x star divided by xk minus x star snom to the power 1. Right. What is this equal to? So as you can see, this value will be equal to k plus 1 to the power k plus 1 upon k to the power k. Alright, which can further be written as k by k plus 1 to the power k, 1 upon k plus 1. Here our limit is k tends to infinity, limit k tends to infinity. So it's a now one of this is a standard result in calculus, that is limit k tends to let's say let t tends to infinity, t upon t plus 1 to the power t is equal to 1 upon the Euler number. So this is because you can see this term is closer to 1 from negative side, and this goes to infinity. So it turns out that this whole term converges to a finite number, which is given by 1 to the power e, 1 upon e. So we'll use this result here, which means it will become 1 upon e, and as you can see 1 upon k plus 1, where k tends to infinity, becomes 0. So this whole limit is 0. Now let us look at the quadratic term. So basically, limit k tends to infinity, xk plus 1 minus x star norm upon xk upon minus x star norm to the power 2. Let us calculate this. This is k to the power 2k upon k plus 1 to the power k plus 1, limit k tends to infinity. This will be equal to k upon k plus 1 the whole to the power k plus 1. Alright, limit k tending to infinity into k to the power k minus 1. Alright, is this correct? I think it's correct. So we can again use the same result. This again goes to 1 upon e, and you can see this goes to infinity because k is in the numerator and k and its both power goes to infinity, so this goes to infinity, which means the second order result that we saw goes to infinity, which means this xk is shows superlinear convergence. It's not quadratic, it's neither linear, so it's superlinear convergence. Okay. Now, to analyze the convergence of the functions, sometimes error functions are used. Error function is basically more generally, normally it is like something like how much is the distance, or let's say xk is your current iteration and x star is your the local minimum. Then this is somehow the error is generally perceived, but it can be anything. So error is just a function of xk. It's a real valued function, so basically you give it xk and it will give you a real number for each position. All right, so but it is very useful in analyzing the convergence of an algorithm. It simplifies it. So let's look at that, the use of error functions. All right, so suppose the sequence xk converges to x star. Let e be a function, real valued function from Rn to R called error function, and e should be continuous. It should be continuous. So the thing is, convergence properties of xk can be studied by analyzing the convergence properties of exk to ex star. So basically, convergence properties of xk can be studied by analyzing the convergence of exk to ex star. So how fast does exk converges to ex star can help us determine, can give us some estimate of how the convergence of the algorithm happens. And in general, order of convergence, that is P, order of convergence is of a sequence, let's say of xk. A sequence is insensitive to the choice of a error function. So the thing is, if the order doesn't change, generally whatever error function you choose for a function, that is the case. There are some exceptions, but right now let's not consider about them, because generally we don't use those kinds of error functions. Okay, so let's not worry about exceptions as of now. Now, so this is what we have tried to answer. Two things we discussed till now. One was what can be the stopping condition, and the other was the convergence. What are the convergence? What are the different types of convergence of an algorithm, like linear convergence, quadratic convergence, superlinear convergence, etc. Now, based on this new information that we have gathered, how does the unconstrained minimization algorithm changes? Let's update it. Unconstrained minimization algorithm. Let's update it. Yeah, so this was the algorithm that we discussed before discussing at the start of our discussion. Now we'll modify it according to whatever new information we have. So one thing is the stopping condition, right? So we studied about the stopping condition. So we'll remove this generic statement and we'll add some real practical stopping conditions. So basically g of xk, norm of g of xk, basically gradient should be greater than epsilon. If till the time it is greater than some value epsilon, it should keep on finding iterating, right? So this is what we discovered. Now we have this value, we need to initialize it as well. So we'll initialize epsilon also. Okay, so we'll give it some value, some very small value, and we'll go ahead. Also, now because we are using only gradient here, instead of local minima, what we are trying to find is some stationary point, right? This is what we will get with this. Okay, now we definitely answered the stopping condition question. We also tried to answer the convergence rate question. Now what about the other question? So one question was how to find xk plus 1 in the step 2a. How do we find this xk plus 1, right? This was the question. So we'll answer that now. So first thing is find a descent direction dk for f at xk. So find dk, which is the descent direction for the function f at the current point xk. Find descent direction dk for f at xk. Okay. Second thing is, once you find the direction, you take a small step towards that direction. So take a positive step alpha k, which should be greater than 0, along dk such that fxk plus 1 is less than fxk. Correct? So this is what we want. So we find a descent direction tk and take a small step alpha k in that direction, such that um, in the fxk plus 1 is less than xk, where xk plus 1 is xk plus alpha k dk. It's a small so xk plus 1 is just new point when we make a small step in the direction dk of alpha k from xk. All right, so these two steps we have to do to find xk plus 1. So let's look at it visually. So let's say this is xk and we find a new direction dk like this. This is dk. All right, and from that we also have to find a new point xk plus 1. This is alpha k, right? This is equal to xk plus alpha k dk, right? And at this point f xk plus 1 should be less than fxk for that's how we get the xk plus 1 new iteration point. So let's say this is the contour map of some function. Let's say this is the xk point. Here is the xk point, and wait 1 second. And let's say this is the gradient line, gradient plane. So let's say the gradient direction is in this direction gk. This is xk. So any direction on the which makes a obtuse angle with gk is a descent direction. Let's say we assume this as a descent direction, and we take a small step here. This is xk plus 1. All right, so this is how we find the new iteration point. Now as we saw that, but where can we have a descent direction? So descent direction set, if we define so it can be any direction such that the dot product is less than 0. So basically it makes an obtuse angle with the gradient at that point, where gk is gxk. All right, so all these directions, or take any line in this sector maybe, and then that will be a descent direction. There is also a question that can be asked, that which is the best descent direction. We'll come to that later. Now that we have understood how to calculate xk plus 1, how to calculate xk plus 1 in 2a, let's update our optimization algorithm again. Yeah, so here is the algorithm that we updated last time. Now let us update it in which we know how to calculate xk plus 1. So we have to update this step. So let's update it. Let's first remove this generic line and then put put it a little bit down. So what do we do? The first thing we do is find a descent direction. Find dk. All right. For f at xk. So we find a descent direction. Then what is the second point? We find alpha k. Greater than 0 along dk. Alpha k along dk such that f xk plus alpha k dk is less than f xk. All right. If this is true, we have to find alpha k which satisfies this equation, and then we update the iteration. We update it like xk plus 1 is equal to xk plus alpha k dk. All right. This is how we update it. Alright, then again we update the iteration, etc. Rest of the things are same. So this is how we are step by step updating our minimization algorithm. Yeah. Now let us see in this algorithm how do we determine this alpha k, that is step length. So step length determination. So broadly speaking, there are broadly two ways in which you can determine the step length. The first one is exact line search. It's called exact line search. We'll define what it is. So in this method, given a descent direction dk, we determine alpha k by solving the following optimization problem. Where optimization problem is given by alpha k equal to arg min such that alpha is greater than 0 of psi alpha, of the function psi alpha, which is given by which is defined as f xk plus alpha dk. So this is one dimensional optimization problem which we have seen before how to solve them. So basically here alpha is the variable. We find the most optimal value of alpha such that f is minimum for a given xk and dk. Okay. The problem with this approach is it is computationally expensive. So basically you are running an additional optimization problem within a big optimization problem. This is very computationally expensive, even though you'll get the best alpha, but sometimes it is the cost of computing the best alpha outweighs the cost outweighs the cost that we incur when we increase the time required for the algorithm to convert. So that's what. So so to so to solve this problem, the computational problem, there is another method which is called inexact line search. Yeah, so as the name suggests, here we are trying to find the exact alpha for which f is minimum. Here we use some thumb rules rather than the optimization problem, which makes it computationally less expensive. But here choice of alpha k is crucial. So we cannot just choose any alpha k. We'll look at some examples that if we choose a wrong alpha k, even though the value of f is decreasing, it never converges, or it doesn't converge to the local minimum. We'll look at some examples, and then we'll see certain thumb rules or certain rules by which you can choose alpha k appropriately in inexact line search. Okay, so let us look at these examples of that will help us look at why choice of alpha k is very important. So the first example, let's say we want to minimize a very simple function x square. All right. And this is how it will look, I think. 1, 2, -1, -2, and this is x. And this is x. Right. So we can safely say that local and global minima is at x star equal to 0. Correct? This is given. So this is the local minima or global minima. Global and local minimum both. Now let's assume that we take a algorithm such that it gives the sequence of iteration as given here: 1 plus 2 to the power minus k. Let xk with this, and dk, the descent direction at each iteration, be given by -1 to the power k. Okay, so let's look how the iteration proceeds forward. So for k equal to 0, 1, 2, 3, and so on and so forth, what are the values of xk? They are 2 minus 3 by 2. If you look, 5 by 4 minus 9 by 8, and so on. Basically, if I start, it will be 2, then minus 3 by 2 somewhere here, then it will go 5 by 4. 5 by 4 is 1.25, so it will be somewhere here. Then minus 9 by 8 is minus 1.125, so it's just above 1. So let's say this line, dotted line, represents the point at which it cuts f1, then it is just above 1. Alright, and how will f vary? Let's see that. So f will vary like first value will be 4, then 9 by 4 x square, 25 by 16, 81 by 64, etc, etc, etc. So you can see the first observation that we get out of this is that that in each iteration the value of f decreases, definitely, right? The value of f decreases, so f xk plus 1, so you can see this is greater than this is greater than this, so it is keep on going decreasing. So sorry, so fxk plus 1 is smaller for all k equal to 0, 1, 2, right? This is, but the sequence does not converge. Why is that? Because because you can see that for very large values, so even though when f is decreasing, you can see for very large values of k, x oscillates between +1 and -1 for very large k. So what will happen is, as soon as you go for very large value of x, this will keep on iterating between -1 and 1. It will never go below this white dotted line. It will never go below this, which means it will never converge to the actual local minima, even when the value of f is going down. So algorithm does not converge even when f is descending. So what was the problem here? So what was the problem? Let's ask. So why did it not converge? The problem was that the small decrease in function value related to step length. So small decrease in function value relative to step length. So step length was reducing properly, but you can see that even though f was decreasing with each iteration, but the rate at which it was decreasing, in each iteration the decrement went smaller and smaller compared to the step length. So the decrement in f should be good enough. That's one learning from this example. So we should choose such an alpha such that the decrement in f should be significant. It should not be very small. Okay, this is first learning. Let's look at one more example. Example 2. We'll minimize the same function x square. So we can again say that local and global minimum is local and global minimum is at x is equal to x star is equal to 0. I'll just copy the diagram here. Alright, So all right, so just 1 second. Okay, so let's say this is the x squared, and local and global minimum is again at this 0, x equal to 0, x is equal to 0. Now let's say at this time the algorithm is given as xk is equal to 1 plus 2 to the power minus k, and dk is minus 1. It's constant for all k is equal to 0, 1, 2, so on. So what is the sequence of iteration? So xk will be 2, 3 by 2, 5 by 4, 9 by 8, etc. and so on. And what will be dk? F, sorry. Values of f will be 4, 9 by 4, 25 by 16, 81 by 64, so on. So here again we can see that the value of f is decreasing. It's but what will happen is we'll start from 2, then we came to 3 by 2, which is half, then we came to 5 by 4, etc, etc, and you can see that this sequence will converge to 1. It will never go to the local minimum. It will never go below, x will never go below 1. You can see that if here k tends to infinity, then this whole tends to 1, right? Because this goes to 0, right? So and this never goes to local minimum. Now what was the problem now? We can again see that fxk plus 1 was reducing. Fxk was reducing for all iterations. What was the problem now? So the problem now was the step lengths. Were too small relative to initial decrease of f. Okay. So step lengths are very, very small. So this is the another learning. We should choose an alpha such that the step length are significant relative to the initial decrease of f. So these are the two learnings. So now let us define certain conditions which if we follow we'll converge to the local minimum, and we'll avoid these two problems that we have discussed. So let's discuss the inexact line search problem now. Now we have we have thought about what problems can inexact line search go through. Now let's discuss about inexact line search. So the problem that we are trying to solve in line search is, so we have been given a xk fxk. We also have found out descent direction dk. What we are looking for is appropriate alpha, the step length. Okay, now let's say this is the value of f as a function of alpha. So if we change the alpha, so basically it's the value of f along the direction of dk. By changing alpha, we are changing the distance of xk plus 1 from xk along dk. So basically, if this is xk and this is dk, this is alpha, this is xk plus 1. So we are changing this value. And how does f change? This is the graph of that. So let's assume that it changes something like this. Okay, so you can see that this is the interesting area where if we choose alpha in this region, then we'll get fxk plus 1 such that it is less, the value of fxk plus 1 is less than fxk. So this is the interesting area we'll look at. And here is the tangent to that curve. So yeah, so let's write down the learnings that we had in the last two examples. Need to avoid small decrease in function value related to step length, small decrease in f relative to alpha, and second that the second learning that we need to avoid small alphas, small step lengths. Okay, these two things we need to avoid. Now, how can we avoid these two conditions? Avoid these two things. So there are several conditions that have been developed over time to ensure these that we avoid these two conditions. So first one of them is Armijo conditions. Okay. First one is Armijo condition. So Armijo condition ensures sufficient decrease in the function value. So it ensures sufficient decrease in the function value. All right. So what is it? So basically it tries to solve the first condition, that there is a sufficient decrease in the function value, but how does it do it? What are the conditions? So let me copy the diagram once and I'll show you through the copy, paste here, reduce the size. Alright, so this is the Armijo condition. So first we'll define it mathematically maybe, and then we'll show it on the graph. So we define a function phi1 alpha, which is given by f alpha k fx xk plus c1, where c1 is a constant, and alpha gk transpose dk. Okay, so where c1 is some value between 0 and 1. Okay, so basically this is a line. So if alpha is a variable, for a given xk and dk, these two are constants. Please remember, these two are constant for a given. So we have been given a dk, the descent direction, and we also know the xk. So at that point the gradient is also constant. So this is constant, this is some constant, and this is also constant because we are finding it for a given xk, and only alpha is a variable. So this is a straight line. This is a straight line. After defining this, we choose alpha k such that f xk plus alpha k dk is less than equal to phi1 alpha k. This is Armijo condition. What this condition is saying that wait, I'll take some other color. So yeah, so let's this denote the function phi1 alpha. So what does this say? That as the alpha increases, so as it is increasing, the decrement in alpha should also be increases. So basically this decrement in fxk, f value increases with increasing alpha. That's what this condition is showing. So and it has that decrement, it has assumed to be linear, and it is saying that as alpha increases, the decrement in the f value should also increase, and any value for which fx plus 1 is less than this this function value, you can take that alpha, right? So here these two are acceptable places. So these two are in these regions. The value of the function value is less than this function psi1 alpha, right? According to Armijo condition, these are acceptable alphas. So basically these are acceptable alphas. Now this solves the so the decrement in function value should be significant. There is another condition called Goldstein condition. this solves the other problem which we discussed. So this ensures that step length alpha are not too small. So this ensures that. So let me just write the condition and then I'll explain it on the graph. Let me first take a copy of this graph. Yeah. So all right. So the condition that the mathematical condition that it has, we again define a function phi 2 alpha, which is given by fxk plus c2 dot alpha dot gk transpose dk, and where c2 belongs to c21. So this is the condition, and you choose alpha such that alpha k such that fxk plus alpha k dk is greater than equal to phi 2 of alpha k. So this is Goldstein condition, and you can see that the structure is almost the same. It is a linear function of alpha. It's some other constant c2, which is just the range is different. So it's now from c1 to 1 rather than from 0 to 1, and it is positive. So c1, where c1 is the constant used in Armijo condition. So this ensures that the slope is because this is negative, this gk transpose dk is negative, then the slope of this line is more negative compared to the Armijo condition. That's it, that what it wants. That's why this relation is there. Yeah. All right. So yeah, this is called Goldstein condition. So let's plot this. Let's plot this. So while plotting, we can see that alright, so this is phi 2 alpha, alright, and because it has to be greater than what are the acceptable positions for Goldstein condition. So wait a second. Okay. Here, and it has to be greater than alright. So according to Goldstein condition, these are acceptable positions. So for choosing the acceptable alphas, we need to follow both Armijo and Goldstein, so that there is sufficient decrease in function value, and there is the step lengths are also significantly large. They are not very small, and for that reason, alpha k must be chosen in these reasons. It must be the intersection of these two conditions. Right, it should be chosen in these three conditions, these three green areas. Here. All right. So that's that. So these are acceptable lengths, and together they are called Armijo Goldstein condition. So Armijo's Goldstein's condition. So choose alpha k such that phi1, phi2. Okay. So if this is followed, we ensure that the step lengths are not very small, and also there is sufficient decrease in f, and hence if these conditions are followed, in inexact line says the algorithm will converge to a local minima. There is one more triviality that you might see, that these are the local minimas of this function for alpha, and this Goldstein condition misses this line, keeps it above. So Goldstein condition misses these local minimas. So that's one drawback you can say, or one observation that you can say, that Goldstein condition misses the local minimum of let's say phi alpha, or f. This, if we are saying this as phi alpha, it misses the local minimum. There's one more additional condition that is also helpful in a lot of places. It's called Wolfe's condition. So what is this condition? So this ensures sufficient rate of decrease of function value in the given direction. So let me just copy the diagram, and then from there I can explain it to you more easily. So you can see that there is a tangent here. Okay, so this tangent can be represented, the slope of this tangent is given by phi dash naught, right? So what does the Wolfe condition say is that choose alpha k such that the slope of the function is greater than the slope of the slope at the initial point, where C2 belongs to C1 comma 1, where C1 is the constant from the Armijo condition. So what this ensures is let's say this is the slope, then at whichever point we have the same slope, let me just draw it clearly, right? Then at whichever point we have a so let's say this is the desired slope, because the slope at initial has been multiplied by a positive constant C2. So then let's say this is the desired slope. Yeah, then let's say we get the desired slope at this point, right? And similarly we'll get a desired in several other places. Let's say here, here, and that's it. These are the places where we'll get the same points. I'll remove this for simplicity, and we'll get these values. So wherever the slope of the function is greater than these desired slopes, that is an acceptable value, which is here, and here. All right. So this ensures that there is both significant decrement in value of the function, and also the step length is big also. So you can use this with Armijo condition to get desired step length. So this is called Wolfe's condition. You can see by following this, you are not missing the local minimas. You're not missing them in your area, which was the case in the Goldstein condition. So Wolfe condition ensures that you don't miss the local minima of psi alpha. Okay, so this was the discussion on the step length determination. We'll end our lecture today. See you next time. Thank you.